In lecture 21, we're going to have an introduction to time series analysis on data types, spectrum, and periodogram, and how to use Python to generate a periodogram. Right. In the last lecture, we had fun by generating three-dimensional plots, including line plots, surface plots, and in practice, files, and you also tried to do vector and streamline plots. And also we learned how to combine with libraries like Basemap to map data to maps. And this lecture, we will learn something very different, which will be more technical on the types of data analysis. So we learn basic concepts of different data types, section data, time series data, panel data, and also we will learn the idea about time domain and frequency domain. And also plots in the frequency domain, which is called a spectrum or periodogram. And we will use Python, which is SciPy, and how to learn how to generate a periodogram. Right, so what is a time series? So a time series is a data which is a form of a sequence of time. Right? So usually time sequence, it's a time sequence, which means that your data varies with time, right? So usually these time series are equally spaced in time. If not, sometimes they're just not. And you have to do the resampling, which is really straightforward to do with pandas. Right. So for example, for time series, and you've already worked with some of those, including the GDP versus per year, and for example, sales volume versus seasons, and stock price versus day, and weather versus hours are these. So any time variations with time in the x-axis, horizontal axis, whatever you call it, that's a time series, right? For example, you can see that this is a mean daily temperature measured at Fisher River near Dallas in 1988 to 1991. And you can kind of see this very regular structure with high temperature in winter, summer, and low temperature in winter, and with daily and monthly variations as well. So there's internal variation structures in a time series, and the point of analyzing time series is to work out what's causing those variations, and that's every variation has a physical reason behind it. Right? Or you can have other time series like this, which is the monthly total number of pigs slaughtered in Victoria. Right? You can see that you have changes in number of the pigs slaughtered, and you have all these variations. But what does that tell you? I don't know. It's a time series. Right. So why is time series analysis useful? So time series analysis applies different statistical models to explore and model the internal structure of a time series data. For example, any time series, you will have a trend, which is the long-term variation of the time series or the property that we're looking at. And there's other ones like seasonal variations. For example, like temperature, you always have high temperature in the summer, low temperature in the winter, so it's periodic. So that's called seasonal. And whatever residue down there, so what's left by removing the trend and seasonal, what you left is the irregular variations. And some of them times you can see these anomalies in the data set, and you can work out what's going on there. Is there a reason? And what's the analysis of those anomalies and what actions should be taken? If you still remember, the last step of data analysis is take actions, right? So before we start looking at the details of time series, I want to introduce the basic ideas about types of data for one-dimensional series. So we will look at cross-section data, time series, and panel data. So that's a very broad classification of data types. So understanding these types of data is very important before you start to analyze the data. So if you know that what kind of data you're working with, and you have a good idea about what tools should I use to analyze these data, right? For example, let's take a look at cross-section data. So cross-section data, just by the name, means that it's a data set that measured at a fixed point of time. So there's no time information. It's a cross-section, right? So cross-section data does not apply to any variations in time. Right? For example, this is the GDP versus life expectation data set you've been working a lot in previous lectures. And you can see this is the plot we've generated, right? We have a plot GDP per capita versus life expectation at year 2007. Of course, this data set is a bit old, but that's interesting. All right, so you can see that there's interesting relationship between the two, but there's no time variations, right? So if you generate a histogram trying to show the different modes or the distributions of the GDP per capita, and you can see different variations, but that's also every data point is taken at year 2007. So there's no comparisons between different years. That's called a cross-section data. So time series data will be, you will look at one particular variable versus time. For example, if you look at the GDP per capita of China versus varies as a function of time. So you can see that increase of the GDP per capita from 1950 to 2007, right? That's almost like exponential growth. And also you can see the life expectancy follows something similar to that too, right? So time series data, that's something you're looking at one variable versus time. So that's very clear definition of the time series data. Right, so panel data, and sometimes also called longitudinal data. So panel data is a bunch of cross-section data putting together with multiple time points. Right, so this is a good example of panel data is that I have 5 countries. These are BRICS countries that we talked about. And you can see that this is the GDP versus year. So each line is a time series, but I have multiple entities here. Right, so I'm comparing different countries at different years. And so I have both cross-section data and time series putting together. So this is called a panel data or longitudinal data, which means that I have both variations in the time series and also compare with different countries in this way. All right, so properties of time series data. The first idea of looking at the time series is that to understand the variable is respect to time. So that time can be years, months, days, hours, minutes, or even seconds, right? So in signal processing or time series analysis, we call these data points are defined in the time domain, which means that in a line plot, your horizontal axis is time. For example, let's see Python to generate the following signal, or sometimes I call it signal because it's a way that engineers call it, right? So data scientists call these time series and engineers call these signals, which is a simple sine wave in the time domain. So y is a function of t equals to 1.6 times sine 2 pi times t. Right? So to generate this, we've learned using NumPy to generate a time series like this easily. So for example, if I want my time is between 0 to 4, say, seconds with 200 points, and then I generate y is a function of t, and I plot y versus t. So this is the time series I get, right? So you can see that t is in second from 0 to 4, and my signal or my time series yt is a sine wave with 4 periods in this way, right? So here yt is a time series, and in physics and engineering, it's often called signals. As the name stands, yt is also known as time domain signal. So time domain means that everything is plotted versus time, right? So the processing of yt for engineering applications is also known as signal processing, which is basically your everyday life. So all your computers, cell phones, everything, software, hardware, these things are based on signal processing. So, but that's way beyond the course of this course. We're not going to look at that. Right. So let's take a look at details about the property of the time series we just generated. So what does those parameters mean, right? So this is the function yt, and you can see that yt equals to a times sine omega t, and if it's written in this way, so a is the magnitude of that signal, and omega is the angular frequency. And if you know the angular frequency versus the actual frequency, so omega equals 2 pi times f. So f is the frequency here, right? So if we zoom in down here, between 0 to 0.5. And then you can see that my signal is discretized to different points, right? So I'm using a stem plot to do here. So you can see that this is Y0, Y1, Y2, Y3, and all the way to Y200, right? So what the idea happens here is I'm actually taking the value of sine omega t at a discrete time points, T1, T0, T1, T2, T3, all the way, right? So the difference between the horizontal axis here is delta T, which is T2 minus T1. That's called sampling cadence. All right, so 1 over the sampling cadence is called the sampling frequency, right? So that's 1 over delta T, and it's usually T1 over T2 minus T1, because the assumption here is that the time series are equally sampled in the time domain. All right, so now let's take a look at another important concept. It's called frequency domain, right? So now we know that with the signal yt, and we know that it shows a sinusoidal variation with respect to time. It has a magnitude of 1.6, and it has a periodicity of 1 second, or angular frequency of 2 pi, right? So that's the signal versus time. That's called time domain, right? So let's take a look at something different. So now we know that there's another information down here we haven't looked at it, is that the frequency, right? So now this is the relationship between the variation of yt and the time. So if you look at the magnitude versus frequency, and then we got another plot, which looks like this, right? So you can see I got 1 data point. So now my horizontal axis is frequency in hertz, and this is the magnitude of my sine wave, right? So you can see that this is called a frequency domain plot. So what I did to get this is that first, the magnitude in the frequency domain is the magnitude of the sine wave, right? So in the horizontal axis, it's the same location as where the frequency is. So 2 pi angular frequency is corresponding to 1 hertz, right? So if I plot the frequency versus the magnitude of my sine wave, that's called a frequency domain plot. And that frequency domain tells you I have a wave that varies at 1 hertz periodicity and has a magnitude of 1.6. So it's the same idea as this. Is called time domain, and this is called frequency domain. So such kind of magnitude versus frequency plots are called spectrums. So let's take a look at another example of signals with multiple frequencies, because most of the realistic signals have more than 1 frequency, right? So for example, this one has 6 frequencies and changes from 0 frequency to 6 hertz. And the magnitude of each component varies from 1 to 1 over 6, right? So if you write the mathematical form of yt, and that's the equation you have, and you can see that for the 1 hertz variation signal, and the magnitude is 1. For the 2 hertz one, it's 1 over 2, and 3 hertz one, it's 1 over 3, etc., all the way go down to 6. So if we use Python to generate that, so first I generate a NumPy array, use the range function down here, and then n is a NumPy array from 1 to 6. And you can see that frequency is basically n, and magnitude is 1 over n in this way, right? So I generate 1D array of time, and then I generate this form of y using this, and you can see basically that's what I did. And you can use a for loop to do that, which is going to be much easier. So if based on this idea, we plot each component versus its frequency, magnitude versus frequencies, and you can see that 1 hertz, and the magnitude is 1. 2 hertz, magnitude is half. 3 hertz is 1/3, and all the way to 6. So this is called a spectrum, right? So the spectrum, and if you compare the spectrum with the time domain signal, so this is actually yt as a function of time. So you can see that instead of giving you a sine wave or cosine wave alone, it shows something like a sawtooth variation in this way, right? And the frequency spectrum goes much simpler than this one. So this is much more complicated than the frequency. The frequency plot you can clearly see what kind of variations are included in my signal, right? From 1 hertz to 6 hertz in this way, right? So how's that generated? So you can see that in the spectrum, the first of all, 0 frequency, it's 0.5. And then you can see that for each frequency component, so that's from 1 hertz all the way to 6 hertz, and these are the horizontal axis in the frequency domain. All right, so the next one is the corresponding magnitudes are these numbers, and you remap these numbers to the horizontal axis. So this is how a frequency spectrum is generated. So you can see that the time series give you the physical meaning of how something changes with time. And then the frequency spectrum gives you the information of what kind of periodicity do you have in such a signal, right? Which is very useful because sometimes you analyze a signal and you match the periodicities between the signals and you can work out whether they vary because of the same physical reason or different reasons. Right? So the frequency domain, and we look at it, if we plot the magnitude of sine wave as a function of frequency, and that's called a spectrum. And if you're familiar with in engineering applications, and we know that for a sine wave, its power is its magnitude square of its magnitude divided by 2. So if we look at the power of this signal, it will be 1/2 times 1.6 squared equals 1.28, right? So if we plot this magnitude as a function of frequency, and that's called a power spectrum in this way. So magnitude, that's called frequency. Power, that's called power spectrum. All right, so a power spectrum in this way is also known as a periodogram. So the spectrum gives you the magnitude of each wave component as a function of the corresponding frequency. And the power spectrum gives you the wave power of each frequency. And this is also known as a periodogram. So you can see that this is a time domain signal that we've looked at. It has 6 components, looks like a sawtooth. And this is a spectrum because now the magnitudes are basically the magnitude of all the variations. And the power spectrum is 1/2 times the magnitude square in this way. So you can see the horizontal axis goes hertz to the -2, this hertz to the -1. So they're just different measures of how the signal is generated. And this is called a periodogram. So in the rest of the lecture, we will learn how to use Python to generate a periodogram. All right, so generating a periodogram in this way. So we will use the same thing. We will use the signal module from SciPy. So from SciPy, we import signal, right? So we defined the frequency n and magnitude 1/m, the same as that one. And you can see that n equals to 1 to 6. And then we define a time domain in this way, right? So we write to the signal together. And in this way, and we use the signal dot periodogram function to generate the spectrum. So the syntax goes signal dot periodogram. So X is my time series, and Fs is my sampling frequency. Right? So for example, this one, my time series is Y, and my sampling frequency here is 50 hertz. Why is that? It's from here, right? Because I have 4 seconds, 200 points. So my time will be 0.02 seconds, the delta t. So my sample frequency will be 1 divided by 0.02 seconds. That's 50 hertz in this way, right? So you can have other options of generating these time series, and then you can find more descriptions of the periodogram function in the SciPy documentation page here. Right. So let's take a look at this example of how we do that. So for example, just a reminder that if we know the delta t, and how do we know delta t? You know the time cadence of the sampling signal, and 1 divided by the time cadence is the sampling frequency. So what we do here is we need to do the use the periodogram function in this way, right? So in this way, you just estimate the delta t based on your time series. In here, it's 4 seconds divided by 200 points, and that's 0.02 seconds in this way. So the sampling frequency is 1 over 0.02, it's 50 hertz, right? So this is time spacing information. So if it's not generated by a NumPy array, for example, if you got a time series, so this example is very clear because I clearly defined the time, which is from 0 to 4, separated by 200 points. So what if the time is not from such a NumPy array? For example, it's from a pandas column data frame, right? So what shall we do? Which is also very straightforward. So we can do this the same way if you remember in the very beginning. So Fs equals to 1 divided by delta t. So what is delta t? Delta t is the time between 2 data points, right? So because it's all the same, so we just do t1 minus t0. So that's the second data point minus first data point. So why can we do that? Because it's equally sampled. So if you can do 3 minus 2 or 100 minus 99, they're all going to be the same. So the sampling frequency is 50 hertz. Right? So why do we need sampling frequency? Because when you use the periodogram function, you need to specify the frequency, which makes your life easier. You don't have to, which is the option, but if you don't do it, and you need to normalize your frequency after you calculate it, right? So, well, one last thing haven't talked about is that after you call the periodogram function, you got 2 outputs. One is all the frequencies, and the other one is all the power. So that's the power spectrum of the frequencies, right? So if you just plot power versus freaks, and you can get to the power spectrum in this way, all right? So let's take a look at periodograms in Earth science, which is Earth orbit. Right? So the Earth's orbiting the sun, which is not a perfect circle, it's actually an ellipse, right? So there are key parameters called eccentricity, which is how far away it's from a circle, and obliquity, which is the rendering of the dipole to the Earth's spin axis, and also the precession, which is rotation of the spin axis, right? So these parameters called eccentricity, obliquity, and precession varies in different ways because of astrophysical reasons. So one commonly used models for the variations over the last few hundreds of years are published by Lasker et al. In this function, so you can take a look at it. So here I've got the data files for you, so which is called this is the file for the orbital information. So if we use pandas to read it as a CSV, so we print out all the columns. So you can see that I have 4 columns. One is the age, so which is each year in the history, and that's the corresponding eccentricity, obliquity, and precession, right? So based on this, and so these are basically time series, right? Because that's an eccentricity versus year, obliquity versus year, precession versus year. So we can work out the frequency components behind all these informations. So first of all, let's filter the data for the last million years and then plot to the time series, right? So this is my cycles, it's my data frame. So I only want everything that's less than 1 million years, because Ka, so 1,000 Ka is 1 million years. Right? So that's called cycles 1 MA. Right? So if I generate plots, if you still remember, we can use subplots, and we use matplotlib to plot the eccentricity as a function of time, which is age, and obliquity function of time, and precession as a function of time. And you can see that they all have these kind of periodic variations, but seems like they vary at different periods, right? For example, this one varies 1, 2, 3, 4 in 4 peaks in about 400 years. So which means that the period is around 100 years. And this one is much faster, and this one's even faster. right? So you can see that in this data frame, all these orbital parameters are time series. And how do we use Python to get the periodicities in these physical processes? Now, this is how we use periodograms. Right? So for example, in this one, so this is a simple code, use the signal.periodogram function to do it, right? So first of all, let's take a look at the periodicity in the precession data. So first of all, I get the precession column. So I use the column axis of data frame, and to make the periodogram function happier, I first convert it to a NumPy array. So this is, sometimes it's not necessary, but this makes it easier, right? So because it's the signal, the SciPy library is built based on NumPy. So if all the inputs are NumPy arrays, it makes it easier, right? So I got the time, which is basically the first column, which is the column age, Ka. So Ka, the units are Ka. So now first calculate the sampling frequency, which is 1 divided by time 1 minus time 0. Why can I do that? Because it's all equally spaced. You can double check that. All right, so now let's use the signal.periodogram function. So two inputs. The first one is the precession time series. The second one is the sampling frequency. So I got two outputs. One is the frequencies of all the precession data, and also the corresponding power of all those frequency components, right? So now if I do semi-log plots, if you still remember semi-log, so I'm only plotting the y-axis in a logarithm scale. So I'm plotting the power as a function of frequencies calculated using the periodogram. So that's a power spectrum. And I set up all these limits. And this is basically a frequency periodogram I get, right? So it's a little rough to see, but you can still kind of work out that I have about 2 peaks here. So one, this one is very clear, which is goes about, you know, between 10 and about 3 times 10 to the 2. So that's my first frequency. And the second one is a bit tricky because you will see it's about 2 peaks here. But remember that this is a frequency, right? So the 1 over frequency gives you the periodicity. So taking the average, so I get a frequency is around 0.0435. So in this way. So you can get 2, you can try to get 2 peaks. And if you calculate the years or the periodicity, they give you very similar numbers. So let's just take this one, right? So now here I used the XV line, axis vertical line function to generate 2 vertical lines with different colors to mark the peaks in the frequency domain, right? So you can see that the criteria here is that, you know, these average peaks compared to the neighbors, they're all at least, you know, factor of 10 larger because this is a logarithm scale, right? So how do we get in this way? So I estimated these frequencies as 0.04 and 0.05. So if we do the periodicity, I get 23 years and 23K years and 19K years in the variation of precession. So how do I get those estimations? So this is something that you should do, we did to get it, right? So for example, so this is a power spectrum. Let's take a look at it. So in a power spectrum, to identify frequency components, so first I draw vertical lines 1 and 2 here, right? So doesn't need to be exactly accurate. I just need a rough estimation down here. And you can see that the first F1 goes to, is 0.0435. F2 is 0.0526, right? So because these are peak frequencies and we can work out the peak periodicity or the main periodicity in the periodogram is 1 over F1. So the reason I can do that, so you can do this for the F1 is 1 divided by 0.0425. Remember, my unit for F1 is not hertz, it's Ka, right? So the F frequency is in the unit of Ka to the minus 1. So if I do this calculation, I basically get 23.5 Ka. So that's the periodicity in the precession data. Right. So this is how you generate, you get back from the frequency domain to the time series. So now after this analysis, that you know there are two driving frequencies or two main frequencies. We sometimes call modes. Two modes in the time series. One is 23.5 Ka, and the other one is about 19. Right. So I'll leave the eccentricity and obliquity as exercise problems and homeworks for you to play with the periodogram. So the key point here is that you need to get the data, get a time series data, and compute the sampling frequency. So if you don't do this, and Python will default regard your time series as separated by seconds. So then you have to do a normalization based on the time property of time series. So I would recommend you every time you use the periodogram, calculate just the sampling frequency and use it as an input in this way. All right. So this is about all we need to know about time series.